In this video, we'll be talking about periodic motion and eventually get to a special case of periodic motion called simple harmonic motion. So periodic motion is just motion that repeats itself. It's motion that repeats over and over. And each repeated motion is called an oscillation, okay, or a cycle. Or if you happen to be going in a circle, it may be a revolution. And the example that we're going to keep coming back to in deriving all of our equations is a glider. So really just an object on a spring. So a glider on a frictionless surface that's attached to a spring. So a frictionless track. Sometimes this is called an air track, attached to a horizontal spring. Okay, so we want to ignore gravity, so we're not going to look at a vertical spring. Okay, so this is just a spring hooked to something. It's anchored to something like a wall. Then we have our mass or our glider, and there's just a track that it kind of slides back and forth on. And this is often called an air track because you can have a track where you blow air up, and that kind of pushes the object up, reducing the normal force, and that's what makes it effectively frictionless. So we'll define our equilibrium position where the spring is not stretched or compressed and the glider's just sitting there. And then if we were to stretch it and compress it, it would move left and right about this equilibrium position. So for this example, we can do Hooke's law, so Newton's second law, where if we sum up the forces, the only force in the x direction, which controls this object's motion because it's only going to be moving left and right, is a spring force. And so the spring force is, in this case, minus kx. And then if we set that equal to the mass times acceleration using Newton's second law, then we can solve for our acceleration, which determines the motion of our glider. So we get ax equals minus k over m times x. So I want to note some things about this equation. So number one, the acceleration is directly proportional to the displacement. Okay, and this is important. Acceleration proportional to the displacement. So proportional to x. This number in front of x, k over m, or minus k over m, these are both constants. Your spring constant, k, your spring force constant, well, it's a constant, so it doesn't change. Your mass of the glider is also not going to change. And then this minus sign out front, this just tells you that it's a restoring force. So if you have a positive displacement, or you're to the right, your acceleration or spring force will be to the left. And vice versa, if you're to the left and have a negative displacement from equilibrium, then your acceleration and spring force will be to the right. So the minus sign just tells you you'll go in the opposite direction towards equilibrium. So this we will define to be simple harmonic motion. Okay, so you could have motion that is repetitive, that's periodic, but is not proportional to the displacement. So it's not linearly proportional to the displacement. So we'll abbreviate that SHM. And this, so just as a definition, will be periodic motion caused by a restoring force and is directly proportional to the displacement. So if you want to determine if periodic motion is simple harmonic motion, so a special case, then you should be able to express the acceleration as some constant times the displacement. Okay, so it's linearly proportional. So before we go any further and look at periodic motion and simple harmonic motion, we need to look at some terminology and some physical quantities that we'll use in describing that motion. So the first quantity we want to look at is amplitude. So amplitude will give the letter capital A, and it is a type of length, so it is the maximum displacement from equilibrium. So it has units of length. So you may measure it in meters. And then we have a cycle or oscillation. And this is just terminology. So this is one complete round trip. So if you're repeating your motion over and over again, this is one complete round trip before you start over, where you return not only to the same location, but we'll see in a second that you also need to be moving in the same direction. Okay, so you may pass through the same location, but you haven't completed a full round trip yet until you're going in the same direction you were when you started. Okay, so the next quantity is period. We'll give that the letter capital T. And this is something we've seen before. It's the time to complete one cycle or oscillation or revolution if you're going in a circle. Okay, and then we have the frequency. So we have two more. Frequency, we'll give this the letter lowercase f, kind of like friction, but without a subscript. But you should be able to tell its frequency from context. And it will be the number of cycles or oscillations per unit time. So how many times did it oscillate in a given amount of time? And this is going to have units of hertz. So this was named after a man named Hertz. And 1 hertz is equal to 1 cycle per second. Or sometimes this is just written as inverse seconds. So cycle is kind of like a radian in that it just tells you a number of cycles. It doesn't really have a unit. And so a lot of times this is just written as inverse seconds or seconds to the minus first power. And then our last quantity is angular frequency. And before we had angular velocity, and we gave that the Greek letter omega, and we're going to give angular frequency the same omega. Okay, so they're very, very similar. And this is just equal to the frequency times 2 pi. Okay, so they're very similar, just off by a factor of 2 pi. And the units of this will be the same as angular velocity in radians per second. The only thing that you need to keep in mind is angular frequency doesn't necessarily have to be associated with circular motion. It can be periodic motion that's going back and forth in a straight line like we saw with our glider. Really quick, let's talk about the relationship between period and frequency. So they have a nice, easy relationship. The frequency is 1 over the period, and so if you just multiply and solve for the period, it is also 1 over the frequency. So they have a reciprocal relationship, and that means if omega is 2 pi times the frequency, then it is also 2 pi divided by the period. And so I just want to make a quick note before we move on that periodic motion is not necessarily simple harmonic. So we've already seen that. Simple harmonic motion is a special case. However, there are times, for example, if amplitudes are small enough, we can approximate small enough then we may approximate the motion as simple harmonic. So as SHM. And we'll see a case where we can actually do this approximation and see why it works and how it works. So now that we have some terminology, we're going to look at a diagram where we track the motion of our glider as it moves left and right and goes through full oscillations from its amplitude, its furthest distance from the right, to minus the amplitude and then back. So if our glider starts stretched, so it's to the right, and in the middle we have the equilibrium position, and then we're going to look at it kind of in between, halfway to its maximum distance away at the amplitude, and also half the way to minus the amplitude, and see what the motion looks like there. So when it's at the amplitude, this means that it has stopped, so it's no longer moving. You've stretched it, maybe you haven't let it go yet. So at that moment, the velocity is 0. But when the spring is stretched the maximum amount, that means the spring force is maximum. So the acceleration in the x direction is going to be maximum. So acceleration equals a max. But because it's going to the left, it's going to be negative. And then our glider moves a little bit to the left. So maybe it's halfway between the amplitude and its equilibrium position. Well, now the spring isn't stretched quite as much, but it is still stretched, so the acceleration is still to the left. It's just not the maximum anymore. And now we're starting to move, so we have some velocity to the left as well. If we keep going, our glider will end up back at the equilibrium position. And when it's at the equilibrium position, it's neither stretched nor compressed. So that means the spring force is 0. And since that was the only force in the x direction, that means our acceleration must also be 0. So now our velocity, we have been accelerating this whole time, and now we're going to stop accelerating. So since we've stopped accelerating, this is as fast as we're going to go. So this is Vmax, our maximum velocity. Then we'll go a little bit further. We're kind of gonna overshoot equilibrium and keep going. But now the spring is compressed in the other direction. So now the force is also going to be in the other direction. So now the acceleration is going to flip, and it's going to point back towards equilibrium. But we're still moving to the left. But since we're accelerating to the right and moving to the left, now we're going to start slowing down again. Okay, and then we end up at the furthest distance away, but in the opposite direction. And here again, the spring is compressed its maximum amount, so the acceleration is going to be maximum again, but now it's positive because it's going to be in the positive x direction. And again, we're going to stop, so our velocity at this point will be 0. Okay, let's keep going. We're going to get back to this position. And our acceleration, again, we're still compressed. So the acceleration will still be towards the right. But now we've started moving again, and now we're moving toward the right. So we have some Vx. Then we get back to equilibrium. The spring's no longer stretched, so our acceleration is equal to 0. And now we have, again, our maximum velocity. And it's positive. So up here, it was actually a negative Vmax since it was going to the left. Then we will overshoot equilibrium again because we're going as fast as we're going to go. And our acceleration, again, now that our spring is stretched, it's going to go back to the left. So AX. And our velocity is still to the right, but it's going to slow down a bit. And then finally, we end up at our amplitude again, our positive amplitude, and we're back where we started. The acceleration is equal to minus a max since it's to the left, and the spring is stretched its maximum amount, and we're going to stop, so V equals 0. Okay, so a couple of things to keep in mind. One, notice that AX is always toward equilibrium. So no matter where we were, the acceleration was in the same direction as the spring force, so it always points toward equilibrium. Okay, and then the other thing is the velocity is 0 when you're at the amplitude plus or minus. So when x is plus or minus a, and then V max is always at equilibrium. Okay, so you accelerate until you get to equilibrium, and then that's as fast as you go, because once you start to overshoot, you'll start to slow down as the force pulls you in the other direction. So V max will always occur at equilibrium. So now we've seen the glider when it's going the fastest, and also when it is going the slowest, but the force and the acceleration are the strongest when the displacement is the largest. So now we're ready to look at energy. So if our system, so our glider and the spring, if there are no non-conservative forces, so things like friction, air resistance, things like that, so no non-conservative forces, that means that our energy, total energy, K plus U, total mechanical energy, is going to be constant. Okay, so we're not going to lose any of our energy, any of our kinetic energy to friction, to heat, or anything like that. And so that means our energy is going to be 1/2 mvx squared. So this is our kinetic energy term, plus we have potential energy from the spring when it's stretched or compressed, and that's going to be 1/2 kx squared. And so this whole thing is also constant. So as we saw before, at certain locations, we know exactly what the energy should be. So when our position is equal to the amplitude, meaning we're as far away from equilibrium as possible, that's also when Vx equals 0. And so if x equals a and Vx equals 0, we can just plug that into our energy equation. So that's going to make the first term, the kinetic energy term, go away, and our energy will be all potential energy, and it'll be equal to 1/2 Ka squared, where we've plugged in a for x. The next point is at x equals 0. So at x equals 0, we're at equilibrium. So this is also where we saw V was equal to V max. So that was our max speed. And that's because all of our energy is kinetic. So at x equals 0, the potential energy term goes away. And all of our energy is kinetic energy. So this velocity is maximum. And then anywhere else, so when we were at halfway in between on either side, well, then the spring was a little bit compressed or a little bit stretched, and we were also moving. So we had both kinetic plus potential energy. Okay, so that's when this is true. And just in general, this is the energy, but at certain locations, we know that one of these terms is going to go away. And so now we have different ways to find the energy of our glider that's oscillating back and forth. If we wanted to actually find the velocity, how would we do that? Well, we can get our velocity as a function of position. So it depends on where we're at. So we can use energy, which we said the total energy is equal to 1/2 Ka squared. So it's worth noting here, if you know the spring constant and you know the amplitude, the maximum displacement, that is sufficient to solve for the total energy. That's all you need. But this is also equal to the energy at any other time. Since it's conserved, it's not going away, and it's constant. Okay, so this just says the energy, the total energy at the amplitude is equal to the total energy anywhere else. Okay, so we didn't just make up an equation, we're just saying that the total energy is equal to the total energy. We just have two different expressions for it. And if we are to solve for Vx, then we can just use this side and this side. So if we solve for Vx, one, our halves are going to go away. And then we have to move our kx squared to the other side. We'll divide by m, take a square root. And what we end up getting, if you go through the algebra, is plus or minus the square root of k over m times the square root of a squared minus x squared. So you could write this all up under the same square root if you wanted to, but you'll see why we don't do this. It's perfectly fine to do it, but a lot of times it's written like this for a very specific reason. And so one thing that we can do is we can take this equation that gives us our velocity at any given point x, and we can see what it is when x equals 0. So at x equals 0, or at equilibrium, we know this will give our maximum velocity. And if you plug in x equals 0, then this goes away and you just have square root of a squared, which is just a. So you get your amplitude out front, and then you still have your square root of k over m. So this is how you could get your maximum velocity. Not only do you get your energy with k and a, but if you know the mass, you can get the maximum velocity pretty easily as well. So it turns out we can relate simple harmonic motion and uniform circular motion that we've already talked about. Okay, so far, we've only been considering a glider that's oscillating left and right. Okay, we haven't looked at circles, but if we're to draw a circle, and then we could put some axes through it. Okay, so this is my x-axis, this is my y-axis, and say we have a particle that is moving around this circle, so it's going around this way. If you were to just track the shadow of this particle as it moves around the circle, it's going to move left, and then it's going to get all the way over here on the other side of the x-axis, and then it's going to start moving to the right. So if you track the motion, we can use what we know about circular motion to get some equations of motion for this shadow that's oscillating back and forth, much like our glider. So our particle is making an angle phi with the x-axis at any given point in time. If phi is equal to 0, then the particle is just along the x-axis. And so if you notice this radius of the circle, that's just going to be the amplitude. So when phi equals 0, it's going to be the furthest away in x that it'll ever be before it starts going back the other way. And likewise, when it's over here, this is as far away as it will get. So the radius is actually the amplitude. Okay? And then we know that the particle, when it's moving in a circle, its tangential velocity, or its velocity, translational velocity, is always tangent to the circle. It's tangent to its path or trajectory. Okay? And so you can also, using some geometry, show that this angle that the tangential velocity makes with the vertical is also equal to phi. Okay, so now let's start getting some equations. So the position of our shadow that's oscillating back and forth is going to be the x position, so the position on the x-axis. That's going to be given by the hypotenuse of this triangle, or the radius, the amplitude, times cosine of this angle phi. Okay, because this is our little triangle, this is our hypotenuse, this is our x-coordinate, this is our position. And so if we just do the opposite side, that's going to give us cosine, and that will give us our x component. Okay, And then we also know that phi is equal to omega t, okay, because angular velocity is just our angle over time, okay, so our angular displacement over time. Okay, so now if we plug that in, we get that the position is given by a cosine omega t. Okay, so now we have our position as a function of time. So this is our first equation. And now we can move on to velocity. So we can use what we know about the tangential velocity. So if you notice, the tangential velocity is going to the left, so it's negative. And then the x component, which is what we're looking for, the component of velocity of our little shadow that's moving left and right, it's going to be given by v tangent. So now we're looking at this triangle where this is v tangent, this is vx, and our angle phi, we could show through geometry, is this angle. So the x component of velocity is now the opposite side, so that's going to be sine of phi, or we already know phi is omega t, but we also know that the tangential velocity is just the omega times the radius, so v equals r omega, but we already said our radius is just the amplitude. So this comes from v equals r omega, okay? And so now, if we plug that in, we can get our expression for velocity. So Vx will just equal minus our minus sign times V tan, which is omega A, and then times our sine omega t. And so finally, acceleration. So this tends to get a little bit cluttered, so I won't write it too much on the circle. If you track our radius, so the radius of this circle, at any given point, while this particle is going around in a circle, it has an acceleration that is inward. Okay, so it has radial acceleration. That's what's keeping it going in a circle. So now, if I just, let me write this on the other side. This is a radial. If this angle is phi, then that means this angle is also phi. And so this forms a right triangle where this is our x component. Okay, so these are just alternate interior angles. Okay, so if you have, this is our angle phi, then this is also our angle phi. Okay, and so we can use that triangle and what we know about radial acceleration to get our acceleration equation. So now we get ax. Again, the acceleration is going to the left, so it's going to be minus a radial, which is our hypotenuse, times cosine now. Cosine is the adjacent side, or gives the adjacent side, of omega t. And then we know a radial is equal to v squared over r, but if you plug in v equals r omega, it can also be written as omega squared times r. And in this case, again, r is equal to the amplitude. So if you take v squared over r and then substitute again v equals r omega, you can get this expression for a radial. Now plugging all of that in, a radial will be omega squared times the amplitude times cosine omega t. This is our third equation. And one thing to notice is a cosine omega t, that's just x. So this can also be written as minus omega squared times x. Okay, the only other thing there is to add, so we have these two equations. Forgot about my 2 on this one. The only other thing is if we wanted to, say we knew the frequency rather than the angular frequency, you could substitute omega equals 2 pi f into these equations, it would get much longer, and there's no really need to do it unless you just have the frequency. This is the more concise way to write it, but you will see it in textbooks where this is substituted in. You could also substitute 2 pi over the period. So sometimes you'll see it in textbooks written like that. But that's just a matter of what you're given. If you ever know the frequency or the period or the angular frequency, you can always get the other one. So you can always go back and forth between equations if you need to. Let's write all of our equations so that we can see all of them at once. Vx is minus omega a sine omega t, and ax is minus omega squared a cosine omega t. Or we just saw, since this is the same thing, this gives that the acceleration is minus omega squared times x. So what you should immediately notice is that the acceleration is directly proportional. I'll put A is directly proportional to x, or the displacement. It's also got a minus sign in front, so that means it's going to be a restoring force. So the acceleration is going to be in the opposite direction of x, and so it's going to push back towards some equilibrium position. So now what we can do is we can take this result that we got from uniform circular motion, and we can match our result from before that we got from using Hooke's law and our glider. So before, we got the acceleration was equal to minus k over m times x. And now we have the acceleration is equal minus omega squared times x. So this must mean, for these to be the same, that omega squared must equal k over m. Okay, so if you just set these two equal to each other, then you could solve. The x's would go away, the minus signs would go away because they're on both sides. And what that gives you is omega is equal to the square root of k over m. So if you remember before, when we got an expression for velocity, we separated our square root of k over m from everything else. And that was because it was going to ultimately end up equaling omega. Okay, so we wanted to separate it from the other piece of the radical. Okay, and since we know we have new expressions for omega, now we can get the frequency and the period. So the frequency is omega divided by 2 pi. And so that must mean that if we substitute in for omega, we get our 1 over 2 pi out front times omega, which is square root of k over m. And then for the period is just 1 over the frequency, so we can just flip everything. So the 1 over 2 pi becomes 2 pi, and the square root of k over m becomes the square root of m over k. So now let's graph some of these so we can know what they look like. So if we graph the position versus time, let me just draw all of these really quick. Acceleration. Our position, say we start at the positive amplitude. So we start up here, and we're going to oscillate. So we're going to go down to equilibrium where x equals 0. And then we're going to go to minus a. And then we're going to come back up. Okay, and then we're just going to go back down. And we're going to oscillate back and forth so it looks like a sine or cosine function. Okay, so if we started at positive amplitude, then our equation is x equals a cosine omega t, what we found before. And the period is the time for one revolution. And so that means we go from one peak to the next peak. Or if you were to pick some point down here, you wouldn't just go till you got to that same height. You would have to keep going until not only were you going to the same location, but you were going in the same direction as well. So this would also be one period. Okay, and so that means the distance between a peak And a trough in this graph would be half a period. Okay, so now if we look at velocity, well, let's match these up. When the position was at its maximum, our velocity was 0. So that's when we stopped, when we got the furthest away. So our velocity is going to start at 0. And then when we're leaving the positive amplitude, we're going to start going back to the left. So we have a negative velocity. So it's going to go down first. And then we're going to pass through equilibrium and reach our maximum value, but in the negative direction. So it goes as low as it's going to go. And then it comes back up, passes through equilibrium again. It will get to its maximum value in the positive direction, and it's going to oscillate as well. And now this was our function. Bx is minus omega times a sine omega t. Okay, so this is a sine function, but instead of going up from 0, it goes down, and that's reflected in the minus sign. So finally, if we look at acceleration, when our position was at the max amplitude, our acceleration was max, but to the left, so it was in the negative direction. So our acceleration is going to start down at its most negative point, and it's going to go up, go to 0 when we're at equilibrium and the spring is no longer stretched. It's going to go maximum and then come back down, and it'll oscillate as well. And this function AX is given by minus omega squared a cosine of omega t. And again, we have a cosine function, so it starts off at its maximum value, but because it's negative, it's going to start off down here, and then it's going to start increasing. So you should be able to compare these to sine and cosine functions and see it is really behaving this way, and then match that with the diagram that we drew representing the glider's motion as it moves left and right. So now we're going to talk about a simple pendulum. So a pendulum is just a mass on a rod that you can assume the rod is massless, and it's just going to swing back and forth. So we have some object on a rod that we can assume is massless, and it has some length. So it has some length L. Okay, and you pull it back some angle theta, and then when you let go, it's going to oscillate back and forth. So it's going to go kind of in an arc, a circular arc. And if we look at the forces that are causing this motion, we have tension in this rod that's keeping it from falling down, and then we have the weight of this mass that's pulling it down. Okay, and so if we continue this line from the rod, this angle theta is the same as the angle that the rod makes with the vertical where it's attached at the roof. And so you can break this into a right triangle. So if we connect it back this way, then this is going to be mg cosine of theta, since it's the adjacent side, and this will be mg sine theta. So if we look at the radial components, or the components along the rod of the pendulum, so radial components, if we were to sum up all the forces, we just have the tension in the rod going up, and we have mg cosine going down, but the ball at the end of the pendulum isn't accelerating in either of those directions, so toward the rod or away from the rod. So the acceleration is 0, and we just find that the tension in the rod must be equal and opposite to mg cosine theta. Okay, so now we can look at the tangential components, and these are the interesting ones. So the tangential component, this is the one that is causing this motion left and right. So at any given point, the end of the pendulum is moving tangent to this path. So this motion must be caused by this force, mg sine theta. So this force is, first notice it's minus, So when our angle is to the right, our velocity is to the left. So this is minus mg sine theta. And now we can do something called a small angle approximation. And this is something you can plug in your calculator to verify it's true. But for very small angles in radians, sine of theta, so sine of some angle in radians, is roughly equal to that angle in radians. So this is true for small angles. And I'll put in radians. That's really important. If you have your calculator in degrees mode, this won't work. Okay, but if you put in small angles in terms of radians into sine, and then you just look at that number, and they should be fairly close. Well, that allows us to rewrite this. So now we can just replace sine theta with theta. So now again, if we look at this triangle, except if we look at the pendulum itself, the length of the pendulum is going down. And then for very small angles, so for very small thetas, this distance, even though it's an arc of a circle, it is approximately straight. If you zoomed in on it very closely and you were only making a very small angle, then this distance would be roughly straight. And it is your tangent component and your radial component are at right angles. So the length forms our hypotenuse, and the opposite side is our little tangential displacement x. Okay? Well, now if we just look at our definition for sine, sine of theta is equal to opposite over hypotenuse, which in this case would be x over L. But we said sine theta is roughly theta for small angles, so that means this must equal theta. So again, we can do another substitution where we take x over L and we plug it in for theta. Okay, so this gives us F equals minus mg x over L, or we can write this as minus mg over L times x. And again, you should notice that this looks like a force directly proportional to the displacement. And it has a minus sign out front. Okay, so there's a restoring force. The pendulum is going to keep going toward equilibrium. And the force, and thus the acceleration, is going to be proportional to the displacement. So this is an example of how we can take something that is not linear. Okay, this sine function is not linear, but we can approximate it for small angles and show that the behavior is roughly simple harmonic motion. So we can use what we know about simple harmonic motion to describe a simple pendulum as long as our angles are small. So if we continue looking at a simple pendulum, now we can compare to what we already know. So before we had F equals minus kx, this was just our spring force for our glider, and now we have F equals minus mg over L times x. So this tells us that for a pendulum, mg over L must play the role of a spring constant. Okay, so it plays the role of k for a pendulum. So before we had omega equals square root of k over m. If we substitute in for k, we get square root of, again, if k is equal to mg over L, then we'll put mg over L, and then we divide by m. Our m's are just going to cancel, and this is going to leave us with the square root of g over L. So this is our angular frequency for a simple pendulum oscillating through small angles. So we can keep going. So our frequency is omega over 2 pi. So that is 1 over 2 pi, and then we substitute in what we just found for omega, square root of G over L. So this is the frequency for a simple pendulum. And finally, if we know any of these three, we can get the rest of them. And so the last one is the period, and that's just 1 over the frequency. So again, we can just flip everything. Our 2 pi comes up top, and our radical just gets flipped square root of L over G. So this is our equation for that. So one interesting thing to note is the frequency, it doesn't depend on the mass of the pendulum in the same way that dropping two objects, it doesn't matter how massive they are. A massive object will fall just as fast as a less massive object. It's independent of the mass. For a pendulum, the period with which it swings or it falls through this oscillating motion back towards equilibrium depends only on its length. So now we'll talk about damped oscillations briefly. So oscillations in the real world, we know that in reality there's no frictionless surfaces. We have friction, we have air resistance, and so those things are going to take energy away from our system, and so they're never just going to oscillate infinitely like we've been assuming so far. And so damped oscillations are oscillations where energy gets taken away, and we saw that the energy is proportional to the amplitude, and so if the energy gets smaller, that means our amplitude is also going to get smaller. So if this is a function x of t, our position versus time, then we're going to start off with a large amplitude, but as time goes by, we're going to start losing some energy, and our amplitude is going to start decreasing. Okay, so we are losing some energy to damping. So this is what's called an underdamped oscillator. Okay, so it's damped, which means the oscillations are going to decrease, the amplitude is going to decrease, but it's going to oscillate many times before it comes to a stop. So it's damped, but not very much. So there are other kinds of damping. So you can have a situation where there's, say, a whole lot of friction. So imagine if we took our glider on a spring and submerged it in oil or some really viscous fluid, and then we stretched it and released it. Well, it's going to have a hard time moving through that fluid, and so it's just going to slowly kind of crawl its way back to equilibrium. So this is when you have something that is overdamped, or an overdamped oscillator. Okay, so there's kind of too much damping. Okay, it's going to take a long time and it's not even going to oscillate. And then you kind of have a Goldilocks zone where an object comes back to equilibrium as soon as possible, but it does it without oscillating. Okay, so if you had any less damping, it would oscillate. And this is called critically damped. So critically damped oscillator. And this is something that you're familiar with if you drive a car. If you ever hit a bump, some cars that don't have proper shocks will just keep bouncing until they kind of settle back down into some equilibrium position. But what you want is for your shocks to be critically damped. That way when you hit a bump, you come back to your equilibrium position where your car's supposed to sit as soon as possible without bouncing up and down. You don't want it to take too long and you to just be constantly falling and be overdamped, but you also don't want to oscillate forever until you hit another bump and then you're just oscillating over and over again. So you want to be critically damped. So finally, let's talk about driven oscillations. So if you have a damped oscillator, which is practical, that's what we experience in real life. But if you want the oscillations to continue, then that means you need to apply a force, a driving force, often a periodic driving force, in order to keep the system oscillating. And then if you apply that force, your system will oscillate at whatever driving frequency that you apply your force at. Okay, so you may call that some frequency omega, maybe we put a subscript D for driving frequency. And you should think of this kind of like a swing set. So if you were on a swing and you quit kicking your legs and nobody was pushing you, you would go back and forth, but you would slowly settle down and eventually stop. What you want is someone to push you at just the right moment. If they push you at the wrong time, it's not very effective, but if they push you periodically when you get all the way back, then you'll start to go higher and higher, and they will kind of drive you and keep you swinging, keep you oscillating. So another really cool thing that happens is if you were to drive an oscillator at or near what's called its natural frequency. So if you were on a swing, you would just kind of naturally swing at some frequency. Just like a pendulum, if you pull it back and let it go, it will naturally swing at some frequency. If you were to drive the system, so apply a force at that frequency, then the response is much greater. So if you push somebody at just the right moment, they will start to swing much higher than if you just push them right in the middle of their swing when they're passing through, say, the lowest point. Okay, so it's much more useful and you get a much stronger response if you push at their natural frequency. Okay, and this is what's called resonance. Okay, and this is sometimes called the resonance frequency. And resonance can be a very powerful thing. So something you should all look up is the Tacoma bridge collapse. So this occurred, so on a day back in 1940, when the wind was blowing, it was blowing and driving a bridge at just the right frequency that it was causing it to oscillate. So it was resonating at its resonance frequency. And eventually the oscillations or the vibrations kept getting bigger and bigger and bigger. The amplitude kept increasing till eventually the bridge was waving like a fluid and it eventually collapsed. So this is an example of resonance in a bad case, but we can also use resonance to our advantage, and it also shows up in other things like electricity and magnetism that you will see in physics 2. So in the next video, I'll pick out some problems for us to solve involving periodic motion and simple harmonic motion so that we can get comfortable solving all of these different physical quantities and solving some problems using this physics. And I'll see you in the next video.